On lesson 11 on page 481, interpreting graphs. Here is a graph of a family driving on vacation, and this is the amount of fuel that's in their tank. So as you can see, in segment A to B, they are driving and the fuel is going down. And then from B to C, they have stopped. And if you really wanted to, you could read based on the time of day how many hours they stopped for. So you would have to figure that out. We could say that they stopped. And we could guess that each of these is a 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock. So they stopped for probably about half an hour. And then after that stop, it seems that the gas suddenly went back up again. So what they must have done, and they must have added some fuel. And then they were driving again, and then they stopped. But over here, they did not add any fuel because the fuel didn't jump again. And then they were driving, and then they fueled up here. You can see that big jump, and they were driving again. Another thing that we can see from this graph is that the rate at which they were driving was about the same. So if you look at this line segment, and this line segment, it's not like they were using gas much more rapidly in one of them than another. Now you can make arguments about whether the amount of gas you use is actually related to the speed you drive, but it seems that they're using gas at about the same rate, and we can tell that because we can eyeball the fact that these slopes are about the same. If we want to be more specific about exactly how fast the gas is being used, we can take an example like between D and E, this segment of the journey. We can read how many hours have passed. So they started at around 10:30 and they're going to about 2 p.m. So that's 1, 2, 3. About 3.5 hours have passed. And you can also read how much gas they use. So at D, they were at about 60 in fuel. And then by E, they're at about 25 liters in fuel. So we could subtract those two, and we could figure out that their fuel consumption was 35 liters in that time. So if we want to come up with an actual rate, you would have to take the liters divided by the hours. And if you calculate that out, it ends up being 10 liters per hour, at least for this segment over here. So we've actually already answered the questions A, what's happening during the journey? I explained that already. And B, what is the fuel consumption between D and E? It is about 10 liters per hour. Which line segment represents the car being refueled for the second time? So we did that as well. We talked about it being refueled right here between D and E, and how it was refueled again here. So the line GH is representing that. And the last question, or question D, says calculate the total time the car is being driven. So all we have to do is we have to look at what time the journey ended, which was at 17 o'clock over here. And we can count the number of hours since 7 o'clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hours was the journey. 10 hours. If the fuel costs 85 cents per liter, calculate the cost of fuel used for the entire first day. So we're interested in how much gas we've used this entire time. This is a more interesting question because you cannot just look at the amount of gas they started with and the amount of gas they ended with because they actually fueled up partway through the day. And furthermore, they did not use up all the fuel that they had fueled up either. So the most accurate way to do this is to look at each branch of driving and to figure out how much gas was used during that branch. So if we look at the branch A to B, we started with 50 liters and ended up with 20 liters. So we used 30 liters of gas here. If you look at D, we started with 60 liters and ended up with around, I'm going to read this properly here. We ended up with around 25 liters. So if we calculate that properly, 60 minus 25, we end up with 35 liters being used here. And then in the last leg of the journey, we started with 60 liters and we ended up with, and I want to read accurately, so I'm just going to make sure, use a ruler here, 50 liters. So we only used 10 liters of gas in the last leg of the journey. So what we have to do then is add those up, 30, 35, and 10, and we can figure out 65, 75 liters was used. So 75 liters times 85 cents per liter ends up being 63.75 used in gas. That's not how much they spent at the pump, that's how much money's worth of gas they used. So a lot of these examples are asking you to make up a scenario for the graph. To be honest with you, I'm not going to ask you a written response question like that. It is interesting to think about that, but you don't really have answers to check and see if you were right. So I'm going to be honest with you. The type of question that I would ask in this particular class is if I give you a bunch of scenarios and then I ask you to match the graph to the scenario or ask you if the graph makes sense or doesn't make sense. So in order to answer these types of questions, there's just a few things you have to keep in mind, and a lot of it is common sense. So for example, if you have linear graphs, I would expect you to understand that if you have a graph that starts at 0, that you probably have started with like 0 money or 0 graph. Whereas if you had a graph that started higher up, you started with some money or some gas or whatever it is that started. Okay, so that's the first difference I want you to understand. The second difference is that if you have two graphs and one of them looks like this and one of them looks like this, that the steeper graph has a higher rate of increase. And whether that's how fast you're going or how much money you're spending it or using it at a faster rate here than you are here. I know, it's common sense, but I would expect you to know that. Another thing I would expect you to know is that there are some graphs that look like this. They start out slow and then they get really fast. So this is something like, for example, the spread of a virus, or if you're hitting the accelerator on your car, it starts out slow, but then it gets fast a lot quicker. Versus something that gets fast very quickly and then levels out like so. Now, it doesn't mean it stops increasing. It still increases, but it increases at a slower rate up here. So an example for something like this might be, well, how many hours you study for a test. The difference between 0 and 1 hour is like a huge difference to your mark. But by the time you're going to like 3 or 4 hours, yeah, it's going to make a difference to your mark, but it's not going to make a big difference to your mark. So just keeping in mind the differences between those scenarios. Another difference to keep in mind is that you can have graphs that go up suddenly like this, and then they sharply go down. This doesn't really happen a ton in real life. More what you're going to get is if you're throwing a ball, for example, it's going to make like a parabolic arch like that in nature. So do understand that when balls go up in the air and come back down again, it's like the blue one, not the green one. The next thing is that sometimes you can get a wave motion for certain scenarios that goes up and down, like in a smooth curve. So, for example, this might represent the tides that come in and out at the shore, or the ride on a Ferris wheel where you start low and you go up high. The thing I want you to note is that these are smooth curves that happen in nature like that. And something like this, although it can happen, doesn't really happen that often in nature. So just kind of keep that in mind, the different types of curves and in a scenario, what they might represent. I have only assigned this page, not all the written response questions before it, because this page shows you the matching question at the bottom, which is asking you to use common sense and figure out which scenario makes most sense for which graph.